Okay, so I have 31 minutes on my camera of video capability, and I have just consumed a massive amount of coffee. So we're going to see if we can get through sections 2.1 and 2.2 of the book in that amount of time. Really, a lot of these ideas are ideas that we've been playing around with since chapter 1. Excuse me. We're just going to collect them all and make them a little bit more precise. So the basic idea here, so this first section is called derivatives and rates of change. So we'll talk about what the word derivative means in just a minute. The basic idea here is that tangent lines to a graph are they're intimately related to the rate of change of the function. So the tangent line to a graph, say y equals f of x. They're intimately related to the rate of change of the function f of x. Okay, so here's our first definition. Our first definition is the tangent line to the graph of y equals f of x at the point P. Let's give this a coordinate. So A is the x-coordinate, and that means that the y-coordinate is f of a. So the tangent line to the graph y equals f of x at this point P is the line through P, so the line passing through P with slope m, where m is expressed by the following, either of the following ways. It's a limit, we'll say as x goes to a, of the ratio f of x minus f of a over x minus a. That's one way to write it. Equivalently, so these are the same, we could write it in a way that might look a little bit more familiar to our class. We let h be a very small number, and we take the ratio of f of a plus h minus f of a over h. Okay, now these are the same. These are equivalent definitions. Either one of them can be used to calculate this number m, which is the slope of the tangent line to the graph at this point P. Let me give you just a brief idea of why that's true. So here's a function maybe, and here's the point A, and so this point right here is a f of a. And then here's another point x. Okay, so we're going to denote x. It's just a little bit away from a. Now, since it's just a little bit away from a, maybe we'll write it as a plus h. That's a plus a tiny little amount. And so this distance here is equal to h. So this point up here has coordinates x, f of x. This is the graph of y equals f of x. And so either of these ratios is the slope of this line. Okay, so this is the secant line that we've talked a fair amount about. And in either of these, as you let x approach a, that means this point right here is getting closer and closer to being at that value there. This secant line will look more and more like the tangent line to the graph. And if you consider it as this ratio, where you're using a and a plus h, then as h goes to 0, again, this point will get dragged closer and closer to a. And so in both cases, the secant line, when either h is small or this value of x just to the right of a is small, that point on the graph will get closer and closer to the point P. This is P. And so the secant line will look more and more like the tangent line at that point. Okay, so these are our two definitions. Okay, so let's go through two examples where we use each definition. So the first example is let's compute the slope of the tangent line at a equals 1. And so a equals 1 for y equals the function x squared. So in this case, our point P is just the point 1, 1, because if a is 1, then when we square 1, we get 1. So let's use the first definition. So m is equal to the limit, we said, as x approaches a of, so f of x here is x squared, f of x minus f of a over x minus a. This is equal to, so a is 1, so we get the limit as x goes to 1 of f of x minus f of 1 over x minus 1, which is the limit as x goes to 1. So f of x is x squared, f of 1 is just 1, and we're taking x minus 1 like this. Now notice, okay, so here we have to do just a little bit of algebra, x squared minus 1 factors. So this is the limit as x goes to 1 of x plus 1 over x minus 1. And we have x minus 1 in the denominator here. Now the x minus 1 factor here and the x minus 1 factor cancel. And so we're looking at the limit as x goes to 1 of the quantity x plus 1. Well, as x goes to 1, this is just a polynomial, so we know from our limit laws that we can just plug right in. So this is 1 plus 1, so this is 2. Okay? And indeed, if you drew the graph of this function, x squared looks something like that. Here's 1, here's 1, here's the point 1, 1. This line right here will have slope 2. Okay, so that's an example using the first definition, this definition right there. So let's go through another example where we use the second definition. So same question. Let's have a be 3, and we'll have f of x be 3 over x. Okay, so this graph, if you were to draw it, looks something like this. So at 3, we're going to be at height 1, and so this is a function that will pass through that point right there. It'll have an asymptote at x equals 0. It'll look something like this, and then it'll look like that on the other side, just if you were wondering. But we're computing here the slope of this line. So what is the slope of that line? Okay, so let's use our second definition. And that was m is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. Okay, we substitute in what we know here. We're taking the limit as h goes to 0. So we're taking f of a plus h, so that is f of 3 plus h. So that is 3 over over 3 plus h. That's what you get when you plug a plus h into the function f, minus what you get when you plug in 3 into this. So you get you'll get 1 in that case. And then over all of this over h. Okay, so this is a problem that requires us to do a little bit of simplifying. Let's start by taking the numerator of this expression, this ratio, and putting that numerator over this common denominator. So we'll have the limit as h goes to 0 of 3 minus, so we're going to use 3 plus h in our denominator up in the numerator. So in order to put this over a common denominator, we have to do that. 1 is equal to 3 plus h over 3 plus h. So when we simplify this a little bit, we get, so we'll have 3, subtract 3, that'll be, the 3's will cancel, and we'll have a minus h. So we'll have minus h over 3 plus h in the top, divided by h, and so if we simplify a little bit more, so this is, I know, a little bit of algebra, it'll be okay, minus h over, this is a denominator in the numerator, so it comes right downstairs, like that. Now we have a copy of h here and a copy of h as a factor down in the numerator or denominator. And so we have those h's will cancel, and we get minus 1 over 3 plus h. Now this is just a rational function. It's two polynomials, and h being 0 is in the domain of this function. So again, we can just plug right in. So this is minus 1 over 3 plus 0, which is minus a third. So that's the slope of this line, minus a third. So this is using the second definition. Know how to use both definitions. So I will encourage you to go back, pause, go back to the previous example, see how the first definition was applied, and then go back to this example, see how the second definition was applied. And maybe even, if you're feeling ambitious, try switching the two methods for each of these two on your own and making sure that you can absorb these concepts. Okay, so that's the definition of the derivative and a few examples. Let's do a more concrete example. So suppose, so this is another example. Let's let s of t be the distance traveled by some object, any object, at time t. Okay. Then the average velocity from time a to time a plus h is this ratio here. So that's a to a plus h. I just knocked my camera stand. That's okay. It seems like it's okay. And if we take the limit of this is the instantaneous velocity. Instantaneous velocity at time a is what you get when you take the limit as h goes to 0 of this quantity. Okay, so let's do a problem in this. So here's a person, and let's say they're 450 meters up. That's quite a long distance, so be careful. And they throw or toss or just drop an object from here, and we're going to ignore air resistance. So it's well known that the distance traveled under these circumstances by this object at time t is 4.9 times t squared meters. Okay, so after 1 second it would have gone 4.9 meters, and after 2 it would have gone 4.9 times 2 squared, or 4 meters, and so on. So question 1, what is the instantaneous velocity at 5 seconds? Okay, and then question 2, how fast is the object going when it hits the ground? Okay, so 2 questions here. Let's answer them. So I'd like to start off just by saying, well, we can compute the instantaneous velocity for any value of t that we like. Instantaneous velocity at any t value by using the definition we just used. So that is that t value, let's say t equals a, that was our limit as h goes to 0 of s of a plus h minus s of a over h. Okay, let's compute this. This is equal to the limit as h goes to 0 of a plus h squared times 4.9 minus a squared times 4.9 over h. Okay, a little bit of simplification. is required at this point. So we have, well, let's see, let me factor out the 4.9 from each of these. So we get a squared plus 2ah plus h squared minus a squared. That's what you get when you factor the 4.9 and expand this. So now look what happens. A squared and minus a squared, they will cancel. So we will get the limit as h goes to 0, 4.9 of, what do we have here? We have 2ah plus h squared, all of this being divided by h. Now notice there's a common factor of h in here in this product, so that can be canceled. So that is the limit as h goes to 0 of 4.9 times, let's say, 2a plus h. That's after canceling that one h with a copy of h from each of these in that sum. And again, so a is just a number that is being fixed for us, so that will just stay there. In particular, it does not depend on h. And so we can just let h go to 0 in this expression, and so we get the answer 4.9 times 2a, or 9.6a. So this is our instantaneous velocity at t equals a. So if you want to answer question 1, then the instantaneous velocity is just plug in a equals 5 seconds. That was our question. Remember, the question was, what's the instantaneous velocity at 5 seconds? That was the question, right? Yeah, the instantaneous velocity at 5 seconds. So if we plug that in, we get 9.6 times 5. I'm not going to do the math in my head. Whatever number that is, that's the answer. Okay. So that's the answer to question 1. Okay, but I want to keep this in mind here. As we move on to answer question number 2, okay, and that is the question of what is the excuse me, what is the object's speed at impact? Okay, so in order to solve this, we first want to know the answer to the following question. Okay. So we have to solve this. So what is t when we've actually reached a distance of 450 meters? So we have to solve this for t in order to determine when the object hits the ground. So what time impact occurs. So we have to solve this equation for t, because that t value that makes this true will tell us exactly when the object hit the ground. Right? Here, again, just to keep this in mind, so here's the object splattered all over the ground. Here's 450. And so we just want to know the time that happened. And the time that it happened is when s is equal to 450. Oh, no, so t is equal to 450. Sorry, something distracting me. All right, very good. So if we do this, if we solve this, we get t is, well, we'll take the positive one because it's a positive time. So t is going to be equal to the square root of 450 divided by 4.9, which, if we do this, we would compute that it is approximately 9.6 seconds. Okay. Now, so 9.6 seconds is the time it takes to get down to 450 meters, and if we take this value here, now we want to know then what is the instantaneous velocity at 9.6 seconds. So then compute the instantaneous velocity at time equals 9.6 seconds. Okay. But we have our formula for the instantaneous velocity. Remember, the instantaneous velocity, we computed it in the last example, was just equal to 9.6 times t. okay, or 9.6 times a. And so if we plug in 9.6 here, then the answer we get is we get 9.6 times 9.6, so it's 9.6 squared. So this will be the velocity, and of course it will be, a velocity is in meters per second. Again, I don't have my calculator handy, so I'm not gonna do the math there. So it's moving quite fast, okay? You wouldn't want to be the object. Very good. So that's an example of a more concrete application of the derivative. Okay. Now, now here we're going to introduce the derivative function. So the definition, the derivative of f of x at x equals a is, so it's denoted by, so this is what we write. We write this, and it is equal to what we've been talking about all along. It's the limit as h goes to 0 of f of a plus h minus f of a over h. Equivalently, you could also compute this by computing a different limit. This gives you the same answer, but our other definition of the limit, which of the slope of the tangent line, which is this. Okay, so you can compute it in either way. All right, so the thing to notice, and this is absolutely key, is that the tangent line to the graph y equals f of x at the point a, f of a, is the line through this point, a f of a. So it's the line through this point, a f of a, with slope equal to f prime of a. So this is the slope. Okay. So this is another. So you'll recall right at the start of this we said, okay, the tangent line, the slope of the tangent line, is intimately related to the rate of change of a function. And so this is the way of computing the instantaneous rate of change of this function f at x equals a, and it happens to coincide exactly with the slope of the tangent line to the graph at that point. Very good. Okay, let's do a concrete example. So suppose that C, I want to make this the cost to produce, I pulled this example from the book, X yards of a particular fabric. Okay, suppose you're a fabric manufacturer. So if you say you want 1,000 yards, okay, f of 1,000 is the cost to make 1,000 yards of fabric. Okay, so this is just the setup for this question. Okay, so let's just ask a couple of questions. Okay, question 1. What is the meaning of f prime of x? Okay, and in particular, what are the units? So cost, I guess I should give you, is in dollars here. What are the units of f prime of x? Okay, so we think of this as being, so the rate of change of f in this case, so this is the answer to this. The rate of change of f is, I'm going to write this in a slightly different way, just to parallel sort of what the book says. Okay, we use the symbol delta. This is the Greek letter delta. It symbolizes change in calculus. Okay, so when you see this, you should see change. So this is all on the side, by the way. This is lecture material. So delta c over delta x. This expression means the change in the cost over the change in the amount of fabric. Okay. So what we're asking ourselves for the instantaneous rate, so this would be an average rate of change of the cost per amount of fabric. If we let the amount of fabric we're making go to 0 in this expression, then what we get is we get the instantaneous rate of change of this cost function with respect to the amount of fabric. Okay, so what are the units of this? Okay, the units are, well, change in cost, this is dollars, and change in fabric, this is yards. Okay, so the units are dollars per yard. Okay, dollars per yard. Okay, so that's the answer to what are the units of this. And so what would be the meaning of this? So the meaning of this expression, f prime of x, means the, well, let's see, how, it means how cost changes with respect to the amount of fabric. How cost changes with respect to the amount of fabric made. Okay, so let's so that's the answer to question 1. What is the meaning of f prime? But let's ask another question that gets at a little bit more concrete version of that answer. So question 2 is what does f prime of 1,000 equals 9 mean? By the way, I just said f prime. That's typically how we would say it. We would say f prime. So say it with me. 1, 2, 3, f prime. Okay, good. So that's, what does f prime mean? So what this means, this means that at the level of producing 1,000 yards of fabric, the rate of change of the cost is $9 per yard. Okay, so let's write that. At the level of 1,000 yards of fabric production, the cost is changing by $9 per yard. Okay, so what that means, so this is the answer. There's nothing too tricky going on here, but you have to think a little bit about this. So what this means is this means that if you're at the level where you're producing 1,000 yards of fabric, then it's going to cost you about $9 to make 1,001 yards of fabric. So the meaning of this so if you're at the level of 1,000 yards of fabric production, then it will cost about $9 to make 1 more yard of fabric. Okay, so this concept here, this f prime of 1,000, this is usually referred to in business as the marginal cost. Okay, so if you ever see the words marginal cost, that's what this means. The marginal cost at x equals 1,000. Okay, very good. All right, so that was section 2.1. So now let's talk about 2.2. And this is about the derivative as a function. Okay, so here's our definition. The derivative, which we denote it by this, and we say the derivative of f, or we say f prime. The derivative f prime of f, the function f of x, is the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so this is when this exists. Okay. Geometrically speaking, this is the slope of the tangent line. F prime of x equals the slope of the tangent line at the point x, f of x. Okay, so that means if we've got our graph f right here, and we pick a value x, then this line right here, the slope is equal to the derivative of f. So this is the point x, f of x. The slope is the derivative of this. All right, very good. So let's do an example. Do one complicated example, and then we'll move on. I guess it's not too complicated, it's just a little tiny bit of algebra. Okay, so find f prime of x. Okay, so the solution to this is, the answer is the limit. So f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x. You'll get pretty good at this by the end of the term. So let's plug in what we have here. Okay, so f of x plus h means plug in x plus h everywhere you see x here. So this is how this goes. We get x plus h cubed minus x plus h. That's the first part right here. Minus f of x. So that is minus x cubed minus x. And all of this is over h. Okay, so we're going to have to do a little bit of simplifying. So hopefully it's not too big of a deal for you guys to do this. I'll leave the details for you, but this is how x plus h cubed expands. It expands just like that. And then minus x minus h, and then we have minus x cubed, and then minus x, so plus x. All right, so a little bit of a scary expression, but I think we'll find that we get some nice canceling here. X cubed is with a positive sign here and a negative sign there, so those will go away. X is with a positive sign here, and there's a minus x right there, so that will go away. So let's rewrite this after we get our little preliminary cancellation. We get 3x squared h plus 3xh squared plus h cubed minus h, and everything else is gone, and we divide by h. Okay. Now every piece of the numerator here has a factor of h inside of it, so let us cancel. Okay, so I apologize. Right around the time where we were about to cancel everything here, my video cut out. So apparently I couldn't do it in under 30 minutes. But anyway, here's what happens in this question. So we have this factor of h in the numerator and a factor of h in the denominator. After we cancel, we're left with this expression right here. Okay, and now this is just a polynomial. X does not depend on h in any way, and so we can just allow h to go to 0 in this limit. So if we do that, we get 3x squared minus 1, and so that is the answer to this question. Find the derivative. So just a little bit of algebra, and then taking a very simple limit. That's illustrating this. Okay, let's just talk about notation for the derivative here. So we have some notation. The derivative comes in many forms. So any of the following expressions is equivalent to the derivative. So we will sometimes write f prime of x. So that's f prime of x is how we say that, okay? Or we might write y prime, so this is for y equals f of x. Or we might write, you might see the expression dy dx, you might see the expression df dx, you might even see something that looks like this. Okay, f in parentheses with a d over dx next to it. So what this means is take a derivative. So for instance, we would write, so for example, we would write something like d dx of x cubed minus x is equal to 3x squared minus 1. So that was what we did in the last example. Okay, but any of these I would expect you to know. So know these terms. Okay. Another definition here. We say that so definition, f of x is called differentiable so say it with me, differentiable at x equals a, if f prime of a exists. Okay, f is differentiable on the open interval AB if f prime exists for all values between a and b. Okay. And this interval AB can be infinite. It can be the interval from minus infinity to infinity, or the interval from a to infinity, or the interval from minus infinity to b. Any of these. So a and b don't have to be finite in order for us to talk about a function being differentiable on the interval from a to b. Okay, so let's look at an example. Where is the function absolute value of x differentiable? Okay, so the answer to this question is to find all of the x values where f of x is differentiable. So let's consider a couple of different cases. Okay, we know what the graph of this looks like. It looks like this. Okay, so you might guess, based on just looking at the graph, that this function is differentiable everywhere except at x equals 0, because right here it seems to have a well-defined slope everywhere, and then when x is positive it also seems to have a well-defined slope everywhere, but right here it seems difficult to put a tangent line there, because how do you situate a tangent line? It's a sharp corner. And we will see that that's the case. So we consider the cases. X is positive, that's case 1. X is negative, that's case 2. And x is 0, that's case 3. Okay, so let's look first at case 1. So x is positive. So remember, the derivative is the limit as h goes to 0 of f of x plus h minus f of x, okay, over h. So we take, but when x is positive, then excuse me, when x is positive, then we know that the absolute value of x is just equal to x. So we can replace this expression by the limit as h goes to 0 of, so we have x plus h absolute value minus the absolute value of x over h. these are all positive numbers inside of these absolute values, so we can just remove them. So we get x plus h minus x over h, which in turn is the limit as h goes to 0. So the x's cancel in this case, and we have h over h, which is just 1. So this is the limit as h goes to 0 of the constant function 1. There's no h's in there, so it doesn't depend on anything, so we get 1, okay? So this means that whenever x is positive, so the derivative exists. So f is differentiable on the open interval from 0 to infinity. Okay, so that's part 1. Okay, you can do exactly the same thing for the case when x is negative. So x is negative. That means that the absolute value of x is equal to minus x. Okay, and so if we're looking for the derivative at x in the case when x is negative, again, it's the same calculation as in the last example. We get that, and then we have to take the negative of these numbers because this number here will be negative. H, we think of h as being a very small number in this case, so if x is negative and h is very small, then this will still be a negative number. So we take the negative of that number, minus x minus h, and then minus the absolute value of x, that would be minus minus x, so that's plus x over h. And in this case we get, well, the x's will cancel. H and minus h here will give us a minus 1. So this will be the limit as h goes to 0 of minus 1, which is just minus 1. Okay. So that's a number, so it's well defined, and therefore the f of x is differentiable. I just write diff for differentiable on minus infinity to 0. Okay, so we verified then that so far we're differentiable everywhere but x equals 0. Okay, so f is differentiable as long as you're to the left of 0 or as long as you're to the right of 0. So this leaves us with case 3 when x is equal to 0. So we're looking at the following question. So the limit as h goes to 0, so f prime of 0, and we're checking to see if it exists, is the absolute value of 0 plus h minus the absolute value of 0 over h. Okay, well, there's lots of zeros here, so this just looks like this. Okay, so we're taking the limit as h goes to 0 of this function. Now notice, okay, this has two different values depending on whether you go from the left or from the right. So if we go to 0 from the right-hand side, then that means that h is positive, and so the absolute value of h is just equal to h. So we get h over h as h goes to 0, which is 1. Okay, so this is from the right. From the left, it's the opposite. So when we're coming at 0 from the left-hand side, h is a negative number, and so the absolute value of it will be equal to minus h, and so this is minus 1 from the left. Okay, so that means that when we're computing this limit here, we get a different answer from the right-hand side as we do from the left-hand side. So that means the left and right-hand limits don't agree. So the limit doesn't exist. Because the two one-sided limits do not agree. So that means that f prime of 0 does not exist. So f is not differentiable at x equals 0. Okay, so the conclusion then is in fact that this is the answer. That f is differentiable on the interval from minus infinity to 0 together with the interval from 0 to infinity, but not at x equals 0. Okay, and that's reflected in the fact that the graph had a sharp corner at that point. So let's talk for a minute about geometric conditions for when the derivative exists. Geometric conditions for when the limit exists. Okay. Or maybe I should say does not exist. Okay. So we're going to talk about this now. There are basically just 3. So here's condition 1. My pen is all gloopy. Okay, so here's condition 1. If our graph has a sharp corner, so here's a graph right there. The limit doesn't exist, or the f is not differentiable here because of this sharp corner. So that was exactly the behavior we saw in the last example. And then, okay, so 2. If the graph of your function has one point where the tangent line is vertical, so f prime does not exist here because the tangent line is vertical. Whenever you have a vertical tangent line, the slope of a vertical line is not defined. and so if your graph has one point where there's a vertical tangent line, it can't be differentiable. At that point. And then there's a third condition, which amounts to the function having a jump. So suppose that our graph has a jump to it. There's no way to define the derivative here. So f is not differentiable here. Okay. And the reason for that is, well, I mean, the tangent line wants to have one sort of behavior right there and another sort of behavior right there. So we're not differentiable in any of these cases. All right. Now something to think about is the following theorem. I'm going to end this discussion with the following theorem. We're not going to prove this theorem, but we're going to state it. So if f of x is differentiable, at a, then f is continuous at a. Okay. So that means that if you can draw a tangent line, then you can draw the graph at that point without lifting your pencil. Okay. I want to underscore the following point, but the converse direction of this is not true. It's not true. Okay. So what do I mean by the converse? The converse, this means that, that if f is continuous at A, then f is differentiable at A. Okay. So notice how we flip these. So if f is differentiable at A, then f is continuous at A. That's a true statement always. The converse of this is the other direction, and that is the assumption that if it's continuous at A, then it's differentiable at A, but this is not true, okay? Not true. Why? So why? Here's an example. Back to the example we just considered. The absolute value function. Notice how I just drew the graph of this function without lifting my pencil? This is continuous at 0, because as I drew it, I did not have to lift my pen to draw it. Okay, so this is continuous at 0, but we just saw that it's not differentiable at 0. Okay, so keep this in mind. This is an important distinction. If your function has a derivative at A, then you have to be able to draw the graph at A without lifting your pencil. If, however, the function is not is not differentiable at a point, that does not necessarily mean that it's continuous. All right, I think we are about done. I thought there was one other thing that I wanted to talk about in this section. Let me take a look here. Indeed, there is one other thing, last thing. Higher derivatives. This is just a quick note. We don't necessarily have to stop at taking one derivative. We could take the derivative of f and get f prime. We could take the derivative of f prime and get what we call the second derivative. We could take the derivative of the second derivative and get the third derivative. And so on. Okay. We'll use this notation throughout the rest of the semester and the rest of the year. So that's the end of section 2.2.